Pressure vessels are widely used in engineering applications, and understanding their response to internal pressure is an important part of structural design. In this video, we will create a simplified, thin-walled, cylindrical pressure vessel with shell elements in Creo Simulate and study the structural behavior under internal pressure. We will apply an internal pressure load, define suitable boundary conditions, and learn how to use symmetry constraints to simplify the analysis. So we're going to model 1/8 of the pressure vessel. I'm going to show you step by step how you can do that. So you create a sketch on the front plane. You work in millimeters. Go the inner radius plus half of the thickness, so 500 plus 5, half of the length, and this distance is 250 plus half of the length, half of the thickness. Then you delete the segments and you click on OK. Now remember, we're going to create a surface. By doing that, first we need to create axes, 2 axes, and we're going to revolve this 90 degrees around this axis. So you just click on this, revolve, and choose this axis and write 90 degrees. And when you are done, you hide everything. And then you go to Application Simulate. You go to Refine Model, Shell, and you create a shell with a 10 millimeter thickness, and you choose the surfaces. And as you can see, the surface is in the middle, and the thickness of the shell is symmetric. Now we are going to do a symmetry constraint. Symmetry, choose these lines and mirror. You can do a cyclic too if you want, but I'm going to choose 3 mirror. 1 mirror here, 1 mirror here, and the last mirror is going to be here. Now we are done with our mirror symmetry, and we need to create a coordinate system, cylindrical coordinate system for our boundary condition. We are going to have a boundary condition in this cylindrical surface. The origin is going to be the same as the original coordinate system. Orientation, we are going to select the references ourselves, use this axis for Z direction, and this axis for one of the 2 other directions. Press OK. Now we go to boundary condition for constraint, displacement, choose the inner surface, select the coordinate system that you have done, just right here, click free for radius. So you're going to let the cylindrical surface deform in the radial direction. in the hoop direction and in the longitudinal direction, you're going to lock them or fix them. It's going to be fixed, but in the radial direction, it can be free. Now we're going to apply a pressure, internal pressure, by holding down control, right, -1, -1 megapascal, and now you have the internal pressure. The symmetry, the boundary condition for the cylindrical part, the internal pressure. Now remember the mesh, we are going to, if you auto mesh it, we're only going to see 2 elements. Maybe we want to give it some material, assign material, ferrous, steel, low carbon, and now it's going to be only 2 elements, which is not, even if it's a p element, we are maybe more, it's more common to use h element for us that are used to FEA. Those with FEA background are more used to H element, but this is a P element, but still it's not good enough for our case. So maybe mesh control, maximum element size, and use 100 for the maximum, and choose the surface it and create the mesh now. And you can see this is a good mesh. Close, save the mesh. Go to analysis, create a new study, call it whatever you want, and run the study. This is going to be fast because it's shell element. And we are going to compare the results with the analytical solution. We know that the maximum is a hoop stress that we got 50 megapascal, and the one misses that we calculated is 43. So we go to results, and it's a shell element. You can choose top and bottom megapascal display option. You can perform it, and you can animate it if you want, but I'm not going to do that. So yeah, the cylindrical part, the maximum is somewhere around there, but the cylindrical part that we have calculated, it's somewhere around 44, 45. But the maximum is 77. Yeah, this is how you calculate the stresses that are introduced when you apply an internal pressure load to a thin-walled cylindrical pressure vessel. We can do it, if it's a thin wall, we can do it with shell elements. You can use symmetry in your advantage, and you can use the following boundary condition that I have. You can divide the surface and maybe fix the one part of the cylindrical surface. that are going to represent something, that holding them, that are holding them. But I use the boundary condition for the entire cylindrical part. And you apply the load, you do a good mesh, and you run the study. As easy as that. Yeah. Don't forget to like and subscribe if you learned something. And see you next time.